This presentation is hosted by the Department of Physics and Astronomy and the Brahe Foundation.
So, it's very nice to be here in Uppsala, where I've had many happy experiences and friends. And I'm pleased today to tell you about some unusually exciting developments, I think, in the exploration of a new class of states of matter. These are time crystals. Let me introduce the question to which time crystals are the answer. So, symmetry is a dominant theme in modern physics. It was very helpful in leading to the fundamental equations we use in the description of nature's basic laws. It's also very useful in classifying states of matter and exploring possibilities for behavior of material systems. In both those regards, equally important is the question of symmetry breaking. We often like to postulate that the underlying equations of a system have a higher degree of symmetry than the solutions of interest. And this has been a very, very fruitful theme in physics, as you probably all know. Among symmetries, perhaps the most fundamental of them all is time translation symmetry. Strangely enough, it doesn't seem to have, at least in English, a less than 7-syllable name. So since we'll be talking about it quite a bit, we'll need a convenient name for it. I'll call it simply tau. Maybe in Swedish there's a shorter description, although I very much doubt it. So tau is the principle which instructs us that we can discover eternal laws. It tells us that the form of laws doesn't change with time. It's also connected through Emmy Noether's fundamental theorem to the conservation of energy. So it's a pretty basic symmetry of nature. Now, spontaneous breaking of spatial translation symmetry, of course we also have spatial translation symmetry, which tells us that the laws are the same at different places and is connected to conservation of momentum, is often broken, and in fact almost many common materials, most common materials, like to form crystals at low temperatures, in which space is not homogeneous. There are certain places where atoms are and other places where they're not, and it's an ordered arrangement. And so an infinitesimal translation of the body will take it into something else, which is to say that the body doesn't obey spatial translation symmetry, but only a discrete version. Physicists are accustomed to making analogies and connections between space and time. Of course, the theory of relativity is the ultimate in that, but also in our equations, there are x's and there are t's, and you can see that they play similar roles. Thus, it seems natural to ask whether there are states of matter that correspond to crystals in time, and that's time crystals. So here is an ordinary crystal, which is an ordered array of atoms. A time crystal, what should that be? Well, atoms don't come and go ordinarily, but we can talk about events that are periodic in time. That would be a time crystal. So materials which somehow pulsate or have structured behavior in time, in the most general sense, are time crystals, in the most general sense of that word. So by that criterion, a beating heart is a time crystal. It beats, and so marks time. Any clock is a time crystal. But we don't, for purposes of physics and invoking all the machinery that goes with the concept of spontaneous breaking of symmetry, we want to be a little more selective about what we call a time crystal. A beating heart is not very precise. It requires feeding and maintenance, and it's complicated. We'd like physical time crystals that are worthy of the name, that exhibit spontaneous symmetry breaking and associated phenomena like soft modes, Nambu-Goldstone modes, and transport properties associated with those sorts of things. Need to be better in all those respects. They have to be self-contained. We want them to be simple. If they're not simple, then it's chemistry or biology, not physics. And we want them to be precise. So that leads to the question, is there a reasonable sense in which tau, time translation symmetry, can be broken spontaneously? Are there material systems in which that happens? This turns out to be a subtle question, which has, however, recently borne some spectacular fruit, which I'll describe to you. And I think it's fair to say that the answer is clearly yes. This, in fact, is a picture of a time crystal. Actually, it's not a picture of a time crystal. It's the picture that accompanied the announcement that time crystals actually exist last October in Science Alert. And here is kind of the more official version when the discovery papers were actually published very recently in the 9 March 2017 issue of Nature, which has a beautiful picture, also completely fictitious, of a time crystal. Inside it has 2 discovery papers and also 2 news articles, technical and less technical, about those discoveries. Usually, discoveries in physics take several years, sometimes decades, before they reach commercial applications, but time crystals have short-circuited that process, and they're all ready for sale. So, let me discuss physical time crystals. I'll first survey what's out there and then make a more detailed, specific description of these new experiments. So there are 3 classes, I would say, of existing time crystals that I want to discuss. Josephson time crystals, Floquet time crystals, and prethermal time crystals. So I will discuss those. Oh, and a 4th, open time crystals, which is closely related to the prethermal time crystals. So I'll discuss all those in turn. An inspiring example, which really was at the front of my mind when I started thinking about time crystals, the possibility of time crystals, is the A.C. Josephson effect. I put an asterisk next to the example for reasons that will appear through the discussion. Let me briefly remind you what the A.C. Josephson effect is. We have 2 superconductors and an insulating barrier between them so that they are almost independent, but not quite. There's a so-called weak link, a weak coupling between them due to tunneling of the Cooper pairs. Nevertheless, we can describe them as having independent phases and independent numbers of Cooper pairs. Then you can write down an effective Lagrangian that describes this physical situation. The simplest possible, the minimal description of it is that you have a number, which is the relative number of Cooper pairs on the two sides, and the relative phase is conjugate to that, according to the basic principles of quantum mechanics. And so you can incorporate that conjugacy by having the number difference multiplied by the time derivative of the phase. That establishes, if you like, that one is the P and the other is the Q dot in the canonical description. Then there's the energy coupling, which is if the energy is minimized when the phases are equal, but the two things are weakly coupled so that they can vary independently with a finite cost in energy. And then finally, when pairs move across the barrier, if there's a potential difference between the two sides, there's this electric potential energy. So all the rich phenomena of the Josephson effect follow from this very simple Lagrangian. If you vary with respect to vary with respect to delta, you get this equation of motion. This is the equation, this doesn't have V, this is what you'd get even in the absence of a voltage. But if you have a voltage, it appears in the equation you get by varying n, which is basically the Schrödinger equation for the phase of the condensate wave function, relative phase of the condensate wave functions in the two superconductors. If you combine these two equations, it's very easy to solve them. And if you solve them, you find that the relative phase, changes with time in a way that's linearly proportional to the voltage. And then that the resulting current, according to the first relationship, is some constant times a sine wave. This, if you think about it, it represents an oscillating current. So there's a physical quantity that's changing in time, even though the underlying system is not changing in time. So it's a spontaneous breaking of time translation symmetry. And in the scheme of spontaneous symmetry breaking, one signature is that there should be a soft mode or a Nambu-Goldstone mode, a thing that can vary within the manifold of possible solutions that are related by translating time by different amounts. Okay, so since the underlying equations don't care about that, if one time is a solution, and time plus a constant is also a solution, that's your soft mode. And there it is in the form of delta zero. It's possible to play many variations on the A.C. Josephson effect, and that's a fruitful source of different kinds of phenomena. They're very different in their realization physically, but embody the same fundamental idea. For instance, you can have condensates of neutral particles in the liquid helium superfluids or in cold atom superfluids, and there are many studies of analogous effects in those contexts. We can also vary the geometry. Okay, so coming back to the asterisk, there are several reservations that one could express about this example, and which have been expressed. I'd say all but one is answerable, and let me very briefly go through them. First of all, it's not an autonomous system. There has to be something supplying the voltage. And this reminds me of the famous discussion of Bill Clinton, where he says, well, it depends what the definition of it is. If it, the system, includes the battery, then the whole thing is that system. So that's autonomous. It isn't self-sustained. That is, the battery will eventually run down. If you close the circuit, somewhere there'll be resistance and the battery will run down. Well, you don't need the battery. You just have an ideal capacitor or a spherical junction so that it doesn't radiate, or use the neutral analogs, and this can minimize or theoretically completely eliminate dissipation. It requires additional symmetry. Some people have objected on that ground, but so what? It can't be, well, the reason that that's perhaps objectionable is that if you want to see the flows, those represent flows along the broken symmetry direction. So if the symmetry really isn't broken, you can't observe those flows. So to observe them, you have to probe symmetry breaking, and so if you're observing them all the time, there was no symmetry. But if you observe them intermittently, that's not a problem either. So I don't think any of these reservations are well-founded. However, there's one reservation which is very well-founded, which is that this system is too familiar. We've known about the Josephson effect for a long time. And yes, it's interesting to observe that it breaks time translation symmetry. But in some sense, it's a repackaging of things we already knew. We want examples that are different, that are new states of matter, not the Josephson effect, not things that are so similar to things we've known before. So let's keep going. The recent breakthrough experiments that were advertised on the cover of Nature concern what are called Floquet time crystals. So let me explain what those are. In those systems, there's a periodic driving term. So time translation symmetry is broken from the get-go. However, what happens is that the response of the system is even less symmetric than the driving force. So in the two different examples in the experiments, one has a driving term with some period t, and the response is period doubled. So the response is at twice the time interval. So translation through t is no longer big T is no longer a symmetry. Only translation through twice that period. And in some of the experiments, it's also tripling, 3 times the period. So we violate a discrete version of time translation spontaneously. Here are the two papers. They are quite different in detail, in an interesting way. The first one is a totally controlled 10-spin system. So you know exactly what the Hamiltonian is. In fact, the interactions are, these are separated atoms, so they really don't interact very much at all if you leave them alone. But if you shine lasers on them, bring the atoms into resonance in clever ways, you can manufacture Hamiltonians basically to order, and that's what's done in this 10-spin system. The other is much more naturalistic, less controlled. It involves what are called nitrogen vacancies in diamonds. So you have diamonds, and and you infuse nitrogen into it, and the nitrogen takes up some spaces in in the diamond and leaves a dangling spin. And in these systems, you have millions of spins that are interacting. And they're not so closely controlled, obviously. So there's a nice description in the Nature non-technical article that I would like to call of the simpler of the 10-atom experiment, but the principles are not that different for the other experiment. So I'd like to borrow that description in introducing you to the experiments. So if you have spins and introduce what's called a pi pulse, then you can, if the spins are in the z direction, you can flip them over to the minus z direction and vice versa. So you reverse the spin in the z direction by applying basically e to the I pi sigma y as a unitary evolution operator or exponential of a Hamiltonian. So this is well known in magnetic resonance, the pi pulse. And if you just have a spin and apply a pi pulse, and it's precisely aligned in the z direction, it'll be plus z, plus, minus, plus, minus, plus, minus. The period will have doubled. So that's already less symmetry than the underlying situation, but it's kind of trivial and unstable, so it doesn't deserve to be called a time crystal, because if, for instance, the laser is slightly detuned, so the pi pulse is not quite pi, but pi plus epsilon, then the ordering is completely washed out. The system does not obey this doubling, and well, I'll show you precisely what happens, but things go haywire, so that nice, simple behavior is not stable. However, in a time crystal, you have additional interactions so that the different spins want to synchronize, basically. And then, even if you get things slightly wrong, because, as is typical of phase transitions, because the interactions are dominating external fields, if the fields are small enough, you get this spin flipping as a stable phenomenon and as a symmetry breaking. For this to happen, thermal equilibrium has to be not established. Okay? That is not normal thermal equilibrium. The system in thermal equilibrium should have a unique state as a function of time, but here we have two states that get interchanged after you go through a cycle. So let me explain this, I'll explain this in more detail. So these systems do not thermalize in the normal way. They have extra structure. There are two distinct possibilities that occur even in exactly the same physical circumstances with exactly the same history of things they've been exposed to. So how can it be that the spins manage to synchronize even though the pulse is wrong? It's not a pi pulse. Well, because of the interaction, say it's a ferromagnetic interaction, they all want to point in the same direction. And you also need some disorder in the system so that although your typical spin is in the z, it would be pointing in the z direction, doesn't have the right period to match your faulty pi pulse, there will be some spins because of the disorder which do, and those spins can lead to lead the synchronization. So the interaction gives you the desire to synchronize, the disorder gives you the ability to synchronize. That's the closest I can come to an intuitive discussion of what's underneath this structured equilibrium. Here is a picture showing the physical situation in visual form. So you have spins, and you have an external magnetic field, and then you have also the pi pulse, which flips them. And this is what it actually looks like. You have an array of atoms, and this is Chris Monroe is one of the leading experimenters on this atomic time crystal. This is what the diamond looks like. It's very pretty, with the lasers that implement the effective magnetic field and the pi pulses, and the red objects are the nitrogen vacancy centers being probed by a different frequency of laser light. So let me now go from diagrams and pictures and words and arm waving to things, a little bit more formal description of this situation. A flow-K system, by definition, evolves according to a time-dependent local Hamiltonian that's periodic with some time capital T, some period capital T. In that case, if you look at the evolution that takes you not through an infinitesimal time, but through the complete period, big T, that's a unitary operator that you're applying over and over again in the evolution of this system in its identical form. So it's a unitary operator. You can diagonalize it, and therefore you get flow K, what are called flow K eigenstates. If you look at the flow K eigenstates, they obey this kind of property. And if you take expectation values of anything within these flow K eigenstates, they will be periodic. So for time crystal behavior, you have to talk your way out of these eigenstates, that they don't get realized. So a complete state of flow K eigenstates always exists, and if you could diagonalize and use that basis, you would have no time crystal behavior. But they might not be physically reasonable states. They might involve, specifically, coherent superpositions of macroscopically distinct pieces. That is, they might be as different as dead and alive Schrodinger cats. They are things that don't arise in practice. They can't be prepared experimentally, nor realized by reasonable experimental procedures, dynamics. This consideration is central to the concept of spontaneous symmetry breaking in general. It would always be possible, in principle, to, say in a crystal, to consider the crystal displaced by different amounts, infinitesimally, and to take the superposition of all those as a quantum mechanical state. Then the symmetry wouldn't be broken. It would even lower the energy. But those are not realized in practice, because you're superposing states that are macroscopically different. So physically reasonable states have to satisfy a condition that captures the idea that they're not Schrodinger cat states. And this is the so-called cluster decomposition property here, which says basically that if you take observations at far separated places, you don't have to worry about there are no correlations. Okay, we don't have to worry about what's going on the other side of the moon or in the system. If we make measurements here, we don't have to worry about what's going on very far away. So, for instance, specifically, if we're talking about a ferromagnet as an example of spontaneous symmetry breaking, we could have a state which is up, with all the spins up, or we could have a state with all the spins down. These do satisfy the cluster decomposition property. You can easily convince yourself. But their superposition does not. If you consider specifically, for instance, the possibility of observing a spin up here and a spin down over there, then the product operator vanishes in either the up state or the down state, as does the product of the single operators. But in the up plus down state, although the product vanishes, the single particle expectations don't vanish. So that does not obey the cluster decomposition property. And it's a physically unreasonable state because obviously you would have to make non-local operations to change the up state into the down state, and those are not realizable in practice. You'd have to work on an infinite number of spins at once. So the basic Floquet time crystal recipe in this language is simple. One uses two-step, what is called stroboscopic driving. So one applies one Hamiltonian for a certain interval and a different Hamiltonian for a second interval. Okay, if you applied one Hamiltonian consistently, that would be normal time translation symmetry. But if you apply them in blocks, then it's only the combination period, the total period that is invariant. In the first step, so for the first block of time, you apply what I'll call H sub MBL. MBL stands for many-body localization, and it's a certain kind of Hamiltonian that has very interesting properties, which I'll come to. Its eigenstates are locally ordered with respect to the z direction of spin. It's a Hamiltonian that incorporates these ingredients of ferromagnetic interaction and disorder that I intuitively indicated were what you need to get a time crystal. And then, of this kind. And then secondly, in the second step, you apply the pi pulse, flipping all those spins. So this is what it looks like concretely. The HMBL is the sum of H1 plus H2, which has interactions, ferromagnetic. They could also be anti-ferromagnetic. It's simpler to think about ferromagnetic, and some disorder. And then the pi pulse is what you would have for this H3 if epsilon were 0, by definition. You apply it for such a time that you get a pi pulse if epsilon were 0. But we want to consider something more general. We want to have a system that's robust, that's the interesting case of spontaneous symmetry breaking that can be realized stably. That is a legitimate phase of matter, not a pencil standing on its end. We want to consider non-zero values of this epsilon. So since the many-body localized Hamiltonian involves only the spin in the z direction, its eigenstates are definite configurations of z spin, and with any configuration, you can flip them all and get an eigenstate with some other definite energy, but still an eigenstate. And when you apply the pi pulse, what you do is take one configuration of the Z spins and flip them all over. So you relate one of these eigenstates to the other. And so the flow K eigenstates, the eigenstates of the product of those two operations, is can be just superpositions of those two states, with the spin and the spin in the other direction. Just one plus or minus the other. However, if those two states are macroscopically distinct, if they don't obey the cluster decomposition property, if the superposition doesn't obey the cluster decomposition property, those flow K eigenstates will be unphysical. They'll be Schrodinger cat states. They are not the physical states that are realized. The physical states will have time translation symmetry broken. They will be the eigenstates of H MBL, which is not invariant. Is not equivalent to its flipped version. On the other hand, if you flip twice, of course, you're back to the same thing. So it's a period doubling. In the nitrogen vacancy system, they've also, following a slightly different protocol, and observed period tripling. Here is numerical evidence of the phenomenon. You begin with a mostly spin-up state, use that Hamiltonian that I show you, and apply that for a while, and then apply the pi pulse, and do it again and again and again. And what you find is that the spin in the x direction and the spin in the y direction do thermalize, but the spin in the z direction does not. It exhibits a stable oscillation from one macroscopic value to the other as you go through the two phases of the double period. And this appears to go on forever in the numerical experiments. So it never approaches thermal equilibrium. It stably exhibits this symmetry breaking. So that was theory or numerics. To me, when there are actual experiments, that takes it to another level. So let me show you again from that paper in Nature, a very revealing set of results. First of all, let's turn the interactions off. This is a totally controlled system, the atomic system. We can turn the atoms off for clarity and observe what happens. And so then we just have a system of free spins, okay, with different magnetic environments. The disorder is, if they don't have different magnetic environments, if there's no disorder, then what you get, if you drive it at slightly the wrong period, is beats. Okay, they start with some alignment. You go through this cycle. They have different initial values of the z direction, and they fall out of phase, and you get beats. Because you're not applying exactly a pi pulse, things fall out of sync. And that's what's exhibited on the left here. If you put on disorder, then you don't get beats because the behavior is not repetitive, they just randomize completely. Now, turn the interactions on, and something remarkable happens. If you just go a little bit off the pi pulse, then instead of getting beats, instead of getting the no interaction behavior, you find that you get these guys behaving as if they're one giant spin with the right frequency. Whereas if you do a large detuning, so the driving frequency is far from a pi pulse, then it just thermalizes. Or actually, in this plot, I'm sorry, you can't tell by the naked eye, but there still is some structure, some stable period, doubling period behavior. The thing keeps going up and down. You can sort of see it stabilizing at the end. By varying the detuning and varying the interaction, you can get a phase diagram. And this, to me, is the most dramatic demonstration that we're legitimately talking about a new phase of matter, that you can discuss a phase diagram and phase transitions. You can study as a function of the detuning and as a function of the interaction when this behavior disappears and when it onsets and when it transitions to different kinds of things. So the time crystal occurs if the detuning is not too big and if the interactions are not too small. If the but also not too big. If the interactions are too big, then thermal equilibrium of a normal kind will be enforced by the interactions. If the interactions are very small, that's like the uncoupled case where you get beats and no a trivial insulator. Formally, these many-body localized states are like integrable systems. It's as if you have, the reason you don't get thermal equilibrium is because there are extra emergent conservation laws, but these conservation laws are robust, unlike in ordinary integrable systems. Ordinary integrable systems are very, very special Hamiltonians that have an infinite number of conservation laws, but if you change the Hamiltonian a little bit, all those go away. But the MBL states, if you perturb them a little bit, the conservation laws change, but there are still conservation laws. So the existence of conservation laws is robust, even though the conservation laws change their nature, and they're in general non-local, complicated things, hard to follow in detail. You may wonder what this kind of localization has to do with localization of a more conventional kind in condensed matter physics, Anderson localization. Anderson localization is the phenomenon that in a lattice with some random interactions, some randomness, particles can get trapped. They don't necessarily diffuse through the system. So whereas in a perfect crystal, the eigenstates are spatially extended, the block states. In Anderson, when you have disorder, even though on average things are periodic, the eigenstates are localized in space. That's Anderson's localization. Here, what's happening is very much like that, except that the localization is occurring in phase space. So your system doesn't explore all of phase space. It doesn't have normal ergodic behavior. It doesn't diffuse through phase space. So for our purposes, as if it doesn't diffuse through phase space, thermal equilibrium is not obtained in the normal way. You have incomplete thermal equilibrium. So that is an introduction to these experiments, and that established the possibility of these new phases of matter. Under broader circumstances, one can have not things that don't go on forever, but time crystals that behave for a very exponentially long time, even though they eventually reach complete equilibrium. These are called pre-thermal time crystals, and they are firmly predicted theoretically using Hamiltonians of a similar kind, and theoretically and numerically these are established. So you have a very, very long time in which you get this period doubling or more general kinds of behaviors. But eventually it thermalizes. Eventually the system keeps absorbing energy from the pump and goes crazy. However, these systems can also break continuous time translation symmetry. If you might ask what sets the period is set by the internal structure of the Hamiltonian. As yet, there are no experimental examples of pre-thermal time crystals, but I'm very confident they'll be coming soon. They have been established numerically. Now, the kind of closed systems that lead to pre-thermal time crystals, when coupled to a system that can take out the energy that's being pumped in by the drive, form another class, the open time crystals. So the Floquet time crystals that we talked about establish a kind of quasi-equilibrium with the drive, so they don't absorb energy, but keep going in this structured equilibrium that has two facets. But in a more general circumstance, the quasi-equilibrium states keep absorbing energy, so unless you take it away, they are pre-thermal time crystals, don't last forever, but if you take away the energy that's being absorbed in the right way, you can have systems that go on forever. And these two have not yet been observed, but I'm confident that they will be. At some level, all time crystals are open time crystals, because if nothing else, oscillating systems will emit low-frequency electromagnetic radiation. That might be very slow, but it's enough to take away energy if the energy is not increasing rapidly, if the increase in energy is sufficiently slow. Okay, so this is how a open time crystal looks schematically. You either have Floquet heating or noise. The steady state is a Floquet or pre-thermal time crystal, and if you take away the energy, the Floquet time crystal will remain unperturbed, and it'll still behave as a Floquet time crystal. The pre-thermal time crystal will go into a stable, forever time crystal, including the possibility of breaking continuous time translation symmetry. Okay, so that's a tour of what's out there at present, and I think in the near future. Now I'd like to describe some more general considerations about the nature of the theoretical description of these objects, which is quite interesting. It would be useful, as has been very useful in the theory of crystals and the theory of solids that's based on a transport and so forth that's based on those things. To have a coarse-grained description where you don't have to discuss the Hamiltonians in detail, but can just discuss the symmetry structure in the spirit of Landau-Ginzburg theory. At first sight, this looks like a non-starter, because if you have a dynamical system described by the Hamiltonian, these are the dynamical equations, and if you minimize the energy, the right-hand sides are both zero. So nothing changes. The energy, if you minimize the energy with respect to all the position and all the momentum variables, nothing can move. However, quasi-paradoxically, if you look, instead of a Hamiltonian, you look at a Lagrangian description, that seems quite different. Take this Lagrangian, which is the analog of what you discuss in symmetry breaking for conventional symmetry breaking, not involving time, the sombrero or Mexican hat kind of potential, just now with time derivatives. The energy function is easy to work out, and it is minimized at a non-zero value of the velocity. What's going on? We just proved that that couldn't happen. Well, the point is that even such a simple-looking Lagrangian leads to a Hamiltonian, which is quite unusual. If you look at the energy function of that form, what you're supposed to do to get from our Lagrangian to our Hamiltonian is express that energy in terms of the canonical momentum, which is this thing I've written down here. And that's not so easy to do. If you want to write that energy in terms of that variable, you ask Mathematica to do it. You can't do it by hand. And when you ask Mathematica to do it, you get a surprise. What you find is that the solution is not single-valued. It has this kind of swallowtail, multi-valued and cuspy behavior. So this is not the kind of Hamiltonian you typically find in mechanics books. People shy away in horror from this, especially when they want to do quantum mechanics. What do you do when you have multi-valued Hamiltonians and cusps? And there's a large literature showing that you can't make sense of these things, but in fact you can. So, getting back to our little theorem that nothing could move, that was based on saying that the derivatives were zero, the gradients were zero, but now we know that there are cusps, so the derivatives are ill-defined, and so there's no real paradox. It's just that we were hasty in drawing the conclusion that the energy minimum can't have non-zero motion. As I was alluding to, it's an interesting adventure to quantize systems like this, but that's a better subject for a seminar than a colloquium, and I won't try to describe that here. Let me just say that those kinds of Lagrangians arise naturally in effective theories of accessible systems. In view of the time, I won't belabor this, just to say that one such system is a particle in a strong magnetic field, where, if you think about it, we're familiar with the idea that things keep moving. In the Hall effect, when you have an electric field and a very strong magnetic field, these charged particles move. Okay, so that's an example here of that kind of Lagrangian arising with higher derivatives. Others occur, I think, in an exciting development in the description of circuits. When you have circuits that contain things called gyrators that are the least known passive circuit elements, they're kind of generalized transformers that in the analogy between mechanical and electrical systems introduce the angular momentum. If you have those things and nonlinear elements, you can get these kinds of Lagrangians for circuits, and circuits are things that you can build in a laboratory, explore at low temperatures, and bring out quantum phenomena. So I think this is going to be a legitimate playground for exploring the consequences of these unusual Lagrangians suggested by time crystals. Okay, so I've showed you, I think, an interesting question, some interesting answers. Now I'd like to go back and discuss a new generation of questions that we can pose with greater interest, knowing that the domain of discourse is not empty, that we're actually talking about something when we think about generalizing time crystals and exploring new states of matter associated with spontaneous breaking of time translation symmetry. What are the thermal and electrical properties of these new states of matter? Generally, in the discussion of thermal and electrical responses of solids, a key step is identifying the quasiparticles and then their response and their interactions. Here, the quasiparticles are something new. They're not simply things that you get by diagonalizing the energy. They're not the energy eigenstates, because energy is not conserved anymore. What happens? What is different about that? It's mostly virgin territory. When and where will the pre-thermal and open time crystals be observed? Can one characterize the different phase transitions, get critical exponents, things like that? And in fact, in a few cases, those have been derived. I don't know that they've yet been measured, but they can be. Are there time liquids? Once you start thinking in these directions, okay, you could have events that have a fixed long-range density, but not necessarily a fixed periodicity. Those would be time liquids. Are there time quasicrystals? Okay, you can go on, whatever, time, whatever. Pick your favorite word and add time, and you have an interesting question. But you can also add a word in front of time, which is imaginary time. And this is something that captured my imagination even in the very first paper on the subject. In quantum statistical mechanics, when you want to set up the partition function at a finite temperature, you want e to the minus h times t. The usual evolution operator, e to the minus h times beta, the usual time evolution operator is e to the minus I h times t. So what you can get from one to the other by making time imaginary. So in the description, and theorists will know this, in the description of thermal equilibrium, imaginary time is a very useful tool. And so time, in that sense, gets on the same, gets on the same status as space, specifically in a relativistic system. If you had, when you go to imaginary time, the distinction between the space directions and the time directions is very obscure. The metric is the same in all directions. And so if you have a periodic structure, an ordinary crystal in this higher dimensional system, that corresponds to an imaginary time crystal. So, and there are interesting phenomena potentially associated with that. Another observation, which I think is underexploited and came as a revelation to me just in the last few months, is that imaginary time turns the Schrödinger equation into the diffusion equation. Okay, so if you take I deep psi by dt and take the I into the t, you get a diffusion-like equation. And spontaneous pattern formation and oscillation in reaction diffusion systems is a very rich, well-developed subject, with things like the BZ chemical oscillator system and many others. And for that matter, the beating heart, which we originally discussed, can exhibit very interesting patterns which you don't want to get into that lead to heart attacks and disruption. But they result from disruption in the normal time structure of how the and space-time structure of how the heart beats. And the analogy between reaction diffusion systems that have been very well studied and time crystals in the physics sense of quantum mechanics, I think can very much illuminate these several kinds of questions that are extremely interesting. Can we realize more complex time crystals with several kinds of atomic events? If you do, and you can, obviously you can have more than one kind of event and more than one thing to monitor than just the spin in the z direction. One can also one can start to have very close analogies to the reaction diffusion systems and structure in space. In the existing experiments, the spatial structure is kind of submerged. We're just looking at overall gross properties of the thing. But in principle, you could have correlation of space and time structure and traveling waves of emerging. And here's particularly where the existing literature in reaction diffusion is going to be very fruitful. You can study the defects and topology in these more complex space-time crystals. And as I mentioned, one of the topological defects that is interesting in the beating of the heart is connected with the onset of failure of the heart. So finally, there's a question which journalists are very fond of asking about time crystals. What's their use? And the honest answer is, I don't know. But the semi-honest answer is a little bit different. The one I actually give is that time crystals might provide nice global clocks or even substrates for quantum computing. If you have a quantum computer, just like for an ordinary computer, it's very useful in algorithms to have a global clock so that all the operations can be synchronized. But quantum computers are very delicate. The clock has to be very precise. It has to be gentle. It has to be quantum mechanical. And time crystals are just what the doctor ordered for that application. Metrology, just everyday measurement of time, that when you want it to be really precise, might benefit from relatively simple room temperature superclocks that you can have. Big ones that operate and are very reliable and operate at room temperature and are macroscopic. From a larger perspective, what especially the recent Floquet time crystals show is that by studying this question of spontaneous tau breaking, we're revealing shortcomings in what people thought about equilibrium. Equilibrium doesn't lead to a unique state in this kind of circumstance. There's structure in time, even when you've reached equilibrium, even when things have settled down. And notably, that includes the emergence of robust, self-organized quantum structures in noisy, randomized systems. That's what happened in these time crystals. Okay. Instead of things settling down and being uniquely correlated with the drive, you find that there's extra structure in time, period doubling or period tripling that emerges spontaneously. So major pioneers in this field have been inspired by visions that such self-organized, self-orchestrating structures could provide powerful quantum sensors. This is particularly what interested Misha Lukin, or infrastructure for quantum computing, which is particularly what inspired Norman Yao. Elaborating very slightly on the sensor idea, in a time crystal you have blocks of spins that are acting in a correlated way. In the nitrogen, Lukin was developing and is developing these nitrogen vacancy systems as delicate sensors for temperature or magnetic field, with a variety of applications in mind. If you can make the system dense, have lots of the spins in the same place, and yet those spins are acting as if all in synchrony, all together, as they do in these ordered time crystal states, then you get more sensitive detectors, okay, by a factor of how many spins are correlated. In the quantum computing scenario, as I alluded to already, long-range order can be used to synchronize and stabilize the behavior of qubits if they start to fall out of synchrony, and the thermalization or decoherence of quantum qubits is a major challenge facing quantum computing, so the possibility of getting everybody in sync by putting them in contact with an underlying time crystal is a really tantalizing possibility in that context. So I hope I've convinced you that time translation symmetry is a very interesting question to ask, that it's especially interesting now that we know that the answer is interesting and has been led to some startling experimental developments, and that there are many, many open questions and even potential applications of these new states of matter. Thank you. Okay.
Much thanks for this direction for our research and kind of show how they crystallize. And maybe there are some questions that you would like to ask Frank.
Yes.
Yeah.
I would like to ask about the fundamental interaction that is in the Hamiltonian H3, because the electromagnetic field is acting on the spin. And that goes in.
Oh, let me remind myself what H3 is. Okay. H3 was the pi pulse, if I remember. Yeah.
But my question is, what kind of interaction is behind it? Because here it looks it appears in a simple form, but what is deeper behind it? Is it the Zeeman field that is driving?
Well, the way that this is actually implemented, if that's what you're asking, is by applying laser light to these things, but in principle it could also be an external field. Yeah.
But then it is the Zeeman field of the light that acts on the spin. That's my question. What is behind the interaction?
Yeah, it's the magnetic component of the light that makes the spin move.
Okay.
Yeah.
It needs to be at very low frequency then.
Not necessarily. If you make a short enough pulse, it can be high frequency too. Yeah. What matters is the integrated strength, if you like, the integrated.
And then, Paul had a question?
Yeah. Okay, so thank you very much. Very interesting talk. So my question is periodicity in real states, real crystals.
Yes.
They are accompanied with interesting things that we know very well.
Yes.
There's a parallel states to real states, and we refer to that as reciprocal states.
Yes.
Reciprocal states.
Yes.
The Bruegel zone.
Yes.
The representation of the translation operator with the K.
Yes.
Can you envision that also here?
Oh yes, absolutely. Those are called. And here it's instead of momentum. As in the case of crystals, you have momentum changed into quasi-momentum, and you have band structure and so forth. Here you'll have exactly parallel phenomena, but now involving energy. So you'll have only quasi-energy, and you'll have bands of allowed energy. Reciprocal time is energy, yeah. Right.
So some other question?
So yeah, in the exploration of things like Brillouin zones and the transport properties, and what the quasi-particles and transport properties, I think is going to be very interesting. Yeah, but I don't know what's going to emerge.
Yeah, so we take one more question.
So my question is more related to the fact that how robust is a time crystal when you couple the time crystal to the environment or to external perturbation? How
robust is it? Well, it depends on the realization. That's the kind of question that the phase diagram answers. It tells you how much you can vary things without going to another phase. Now, so of course that only envisages certain kinds of perturbations. You could have if you allow any kind of perturbation, then the only state of matter that you should be talking about is a black hole. That's the ultimate thermal equilibrium. But so the question is, what kinds of perturbations you wish to consider that do justice to the experimental situation. And I think in practice, you can basically, in these controlled small number of atom systems, you can control the Hamiltonian pretty well. However, there's always coupling to the electromagnetic field. There's radiation possible when things are moving around. That has not been included here. And I think it remains to be really carefully studied. That's what the effect of that is. That's related to this question of open time crystals, when you couple things to a bath. My intuition is that not only will be harmless, but actually will be helpful in draining, certainly in the case of Floquet time crystals, it'll be helpful in draining the energy that's maybe slowly being pumped in. In the case of, maybe I should leave it at that. Okay, so, yes, so it's an open-ended question, I guess. It depends what you want to consider part of the system and what you want to consider as its coupling to the environment. But basically, I think with reasonable definitions of those things, you can get pretty robust systems. That's a vague answer, but it's a vague question.
So
Yeah.
I'm not sure if it makes much sense, but can you make sense of an analog of
like long-range order, like long time?
Oh yes, absolutely.
States start to interact over a different time.
No, there is long-range order in time here. It's very important that the phase structure, the correlation does not die out with time. That's the essence of the math. So if we had this two-lobe structure, even over very, very long stretches of time, they don't fall out of sync. So it's very robust. And even if you get, as I said, even if you get the flipping frequency slightly wrong, they still stay in sync. So the robustness, the long-range order is a very, very deep and characteristic property here, which distinguishes it from things like, a long time ago Faraday discussed period doubling when you take a dish of mercury and shake it up and down and look at the waves that develop. You can find period doubling in that circumstance. This is a mechanical system, but that doesn't last forever. It thermalizes, and also it is not phase synchronized over long periods of time. So, yeah.
We have one more question here.
Well, there's another one over there too. So, yeah.
So the fundamental idea of spontaneous breaking of time translation
Yes.
is something that's, as you said, familiar from classical dynamical systems, where there's period doubling in the Bezier reaction or in
Yes.
cellular convection.
Yes, those are reaction diffusion things. Right.
So would you classify those as very basic examples of time crystals? And also, in those examples, period doubling goes on until completely periodic behavior. As you tune the order parameters, you can have chaotic.
Yes.
Do you think this could also happen with the Josephson?
Oh, you better ask that again. But let me ask the first question. Answer the first question first, which is I would say that these reaction diffusion systems and simple mechanical systems display some of the properties we'd like to have in a physical time crystal, but not the full array of properties that we normally would associate with spontaneous symmetry breaking in physics. So whether you want to call them time crystals or not is somewhat a matter of taste. And I don't think as yet there's a general agreement about what the exact definition, and there may never be, of exactly what the definition is. But I think the criteria, the rough criteria that I outlined, you want something that's autonomous, precise, and simple. Well, that's and that has soft modes, and so some of the more detailed things, critical exponents. Those things are the best examples. The sort of the Platonic ideal of time crystals. But then there are other things that are kind of debased versions of time. But I'm really hoping, actually, that we can, the pure cases will exhibit, we can study in the pure cases phenomena that have already been illuminated from the mathematical point of view in these impure cases. In particular, I'm discovering now, as I look at the literature of these reaction diffusion systems, that not only have they studied time-dependent pattern formation, but also defects in the time-dependent pattern formation. And so these are kind of like defects in space-time, and that kind of ordering. And those, that kind of analysis, that style of analysis will also work for, of course, for the physical time crystals, and I think will be very, very interesting. Okay, so we get to steal a lot from the chemists and biologists. Yeah. Yeah.
We know from the X-linear statistics there are some events when the time distribution can be described by a power law fat tail distribution function instead of a Gaussian function, and that if I consider these extreme events, then do we have some corresponding Hamiltonian or Lagrangian to describe these systems, or is it a helpful analogy?
Things with long tails? Well, it's a different subject. I'm not sure what, as far as I know, I mean, there are a variety of mathematical methods to describe statistics with long tails, some of which have a physical kind of overtone in terms of instantons and rare events and things. But as far as I know, that has not brought in ideas about spontaneous symmetry breaking of any kind, let alone time translation symmetry. So I'm not. So there may be something interesting there, but I don't know what it is. Yeah. Okay.
So maybe we thank Frank again for this.